life as we know it is about to change. Once deemed science fiction, controlling machines with your mind and body's electric impulses could be a key to major technological breakthroughs. Whether it is an EKG, which measures electric potentials related to your heartbeat, an EMG, which measures electric potentials from your muscles, or an EEG, which measures electric potentials in your brain, scientists are discovering new ways to harness the human body to transform our lives. Inventive companies like Emotiv have found groundbreaking ways to use small electrical signals from the brain to do everything from controlling electric wheelchairs to playing video games. Similar to how an object has gravitational potential energy due to its location in a gravitational field, a charged particle possesses electric potential energy by virtue of its location in an electric field. Electric potential is the electric potential energy per unit of charge, often referred to as voltage. Charged ions are constantly being separated, setting up electric potentials that can be measured. For example, in EEGs, certain thoughts trigger electric potentials in different regions of the brain. Companies have discovered ways to harness those impulses and use them in cutting-edge technologies. Tomorrow's innovation is beginning today, all because of the electric potential of the mind.
We now move on to discuss electric potential. Recall we just learned that if we have a charge Q move inside electric field, its electric potential energy can change. We thus define the change in electric potential as the change of potential energy of this particle divided by the charge of this particle. To be more specific, if I have a charge Q move from position A to B, is electric potential energy changed by delta PE, then this delta PE divided by Q, the charge of this particle, will give me the electric potential difference between point A and B. Now, there is a huge difference between electric potential and electric potential energy. Electric potential energy is energy carried by the charged particle in the presence of electric field. So electric potential energy can change when the charge moves from location to location. Anyway, it's energy carried by the charged particle. Electric potential, however, is a quantity exists at each point in space and time due to the presence of electric field. The existence of electric potential is independent of whether you have charge moving inside to the electric field. So we have a quantity at each location. We call it electric potential. In this regard, electric potential is very similar to electric field because we said electric field is a quantity exists at each point in space and time, regardless of whether you put a test charge in that location of space and time. Now, of course, there is difference between electric potential and electric field. Electric field is a vector field quantity. Electric potential is a scalar field quantity. So at each location in space and time, there is a value of electric potential associated at that location. So electric potential is a quantity associated with location in space and time. So that's the difference. To put it simple, we say at each location we have a potential. Then we can have what's going to happen if I put a test charge Q at that location. Then that test charge would have electric potential energy, Q times V. Now, if the charge move between an electric potential difference delta V, And then the change of the electric potential energy for the charge is Q times delta V. So because the energy of, sorry, because of the unit for energy is joule, the unit for charge is coulomb, so the unit for potential is 1 joule per coulomb. If we have a uniform electric field, let's recall what's the electric potential energy change. If the charge moves from A to B for a distance d and move in the direction of the electric field, the change of electric potential energy would be given by negative Q E displacement.
Right.
Now, based on the definition, change of potential would be change of electric potential energy divided by charge. So that Q and Q is going to cancel. The change of potential for uniform electric field is given by negative electric field times displacement. Now, think about the position A and B. Which position has higher potential? Which position has lower potential? The positive charge would have higher electric potential energy at position A. As such, location A would have higher electric potential. And the electric field now is always pointing in the direction of decrease of electric potential. If we have a positive charge move inside the electric field, if it moves in the direction of the field, then it moves from a position with higher potential energy to a position with lower potential energy. So its electric potential energy would decrease. Its kinetic energy is going to increase. For point charge, the potential created by point charge at a location, origin location, would be potential equals k q over r. R is the distance from the location of the electric potential is measured to the location of where the point charge is. If we have more than one point charge, then we just need to calculate the electric potential created by each charge at that location and sum the potential created by each charge up. Now, this time, electric potential is a scalar quantity, so we don't need to worry about components of vectors, just to do algebra sum. If we have 2-point charge, then the electric potential energy between those 2-point charge is given by K Q1, Q2 divided by R. R would be the distance between those two charges. If I have more than two charges, then I just need to find out all the pairs of the charges. For example, if I have 3 charges, I'm going to have 3 pairs. Pair 1, 2, pair 1, 3, pair 2, 3. Now, if you add a fourth particle, you can do the math, do the count how many pairs you can have. You're going to have 6 pairs if you have 4 charges. Now let's stay with 3 charges. We have 3 charges, 3 pairs. So the total potential energy of those 3 charged particles is given by the potential energy between Q1 and Q2, which is K Q1 Q2 over R12. The electric potential energy between Q1 Q3, which is K Q1 Q3 divided by R13. And the electric potential energy between Q2 and Q3 is given by K Q2 Q3 over R23. And using the superposition principle, if I have 2-point charge in space, I add the potential created by each of them at each location. That would be how the potential created by 2-point charge looks like.